Swayam Prabha. Digital India. Educated India.
So, hope you had time to kind of reflect on what we were discussing in the last class. So, we were discussing, just to give a very quick summary about side channel attacks, and in particular I was trying to give you an idea about how to perform a side channel attack on the AES algorithm, right. So, essentially we were discussing about how to perform what is called as difference of mean based side channel attacks. Okay. So, in today's class, first we shall try to look at another technique for performing side channel attacks, again using power consumption, which is called as correlation based attacks or CPA. Okay. So, this is a statistical attack, again it falls into the category of differential power analysis, okay, and it's a I would say a more developed method compared to difference of mean. Okay, and so what we will try to understand is how CPA works and how we can extract or reduce the key using CPA or correlation power attacks. Okay, so the CPA, like what we have seen in the previous case, also exploits the fact that power consumption depends upon underlying data. Okay, so the power consumption essentially is a manifestation of the underlying data. So you still try to kind of recover the data, and from there you try to conjure the key, you try to guess the key. Okay. So therefore, right here we are again we try to understand how it works. So just a quick reminder to you, we had this the AES algorithm where we had the plain text which was XORed with the key, and that essentially passed through the different rounds of encryption, right. So these are the rounds that we had for the encryption process. So what we were targeting in the last class, if you remember, was the first round S box, right. So in the first round S box or sub bytes or byte sub, whatever you call, right, we had 16 S boxes because our plain text, so we are talking say with respect to AES 128 where the state is 128 bits, so it can be conceptualized as 16 bytes, and likewise the key. Okay. So we had 16 S boxes, out of which we can target any of these bytes. So without loss of generality, I was targeting this particular S box. Okay. So now we will try to do the same thing in this context also. When you are talking about CPA attack, we will still try to do the same thing. Okay, so we will be say targeting one of these S boxes and say we are targeting this 0th S box, and we will be finding out what is the output of this S box based upon the guess that I do on the key byte. Okay, so this key byte that is of importance here is a 1 byte data. So therefore, right, it can take 256 possible values from 0 to 255. So what I will do is, in particular, I will be trying to find out what is the output of this S box where P0, which is say the 0th byte, combines with K0, which is the 0th byte of the key, and it results in the S box. I mean the S box gives you certain output. Okay. So one thing I would like to mention here on the passing, that I am trying to do the attack like previously also the difference of mean attack I was talking with respect to the plain text, right. You can also reformulate this in a similar manner by processing it from the ciphertext. Okay. So if you want to do it from the ciphertext, what you just need to do is you just need to observe the last step of the AES operation, and therein if you have the cipher again shown over here, like suppose this is your cipher, and I will be focusing again on one of the output cipher bytes, say in this case this one is C0. Okay. I will be, rather than doing S box of P0 XOR K0 like this, we will just do the inverse S box, because the S box is a bijective map, so it has a reversible operation. So I will be like focusing on this step. But in this case K0 will be the 10th round key. Remember that we talked about the key scheduling algorithm where like from the input key you have the first round key, from the first round you have the second round key, you have the third round, and likewise you have got the 10th round key. Okay. Now if you can deduce the 10th round key, then you can actually apply the inverse key scheduling, and from there you can obtain the main key. Okay. So it is equivalent. So what I want to say is that the attack can also be done from the plain text, it can also be done from the ciphertext. Okay. So imagine that as an attacker you have probably more access to the ciphertext and also the corresponding power trace. You can use that information also to recover the key. Okay. But I'm just saying like for simplicity maybe from the plain text. Okay. But you can also reformulate the problem to work from the ciphertext side. Is this point understood? Okay. And you can also note, like for some of you who are interested, that in the AES specification, the last round of the AES specification does not have a mixed column step. Okay, every round had these steps, add round key, sub bytes or byte subs, shift row and mixed columns, but the last round does not have a mixed column step. Okay. We can talk if you are interested offline, like why the last round does not have mixed column. But at this point, just keep in mind that the last round does not have mixed columns. Okay. So anyway, so now what we are doing here is we are focusing on this step, S box P0 XORed with K0, right? And in the difference of mean attack, if you remember, we were in particular focusing on one of the bits of this step. Okay. So like I was explaining with respect to the LSB of this particular evaluation. But now we will be operating on the entire byte. Okay. So the idea here is that what we will try to do is from this particular evaluation, or rather on this evaluation, we will apply a power model. Okay. So the power model is essentially nothing but a simple model which tries to predict the dynamic power consumption of the device based upon this data. Okay, so you know that power consumption in circuits or in VLSI circuits has got two important components. One is the dynamic power, the other part is called as the static power. The dynamic power is the component which depends upon your internal data. And since that is the part that you would like typically to exploit in an attack, we are focusing more on the dynamic power. Okay. So how do you predict the dynamic power? You can see this state, for example, in this case it's a byte, and you can apply your most like favorite power model. Okay, so there are different types of power model. Two very simplistic power models are called as the Hamming weight power model and the Hamming distance power model. So the Hamming weight power model simply means it stands for the number of ones in that byte. Okay, and Hamming distance means it is the change of the state that matters. Okay, what I mean is, like suppose if you have got a state, say I call it as st at time t, and this changes to say st plus 1, right? Then Hamming distance would mean nothing but if I want to calculate the Hamming distance of st and st plus 1, then this is nothing but the Hamming weight of st XORed with st plus 1. Okay, if you take st and you XOR it with st plus 1, then you get the number of changes. Okay, and the Hamming weight of that encoding of the change essentially is nothing but your Hamming distance. Okay, so you can use any of these power models, but again for simplicity I will be using the Hamming weight power model. So which means that I will say that if my state has st at this point, then I will define something which is called as a hypothetical power. Okay, so I will call this as a hypothetical power, and the hypothetical power is nothing but the Hamming weight of st. Okay, the hypothetical power at the time t is nothing but the Hamming weight of st. Okay, and why do I call it as hypothetical? I call it as hypothetical because this estimation depends on the hypothesis that I do on this key, right? Remember I said that this key can take 256 choices. I just start with a guess, right? That is my hypothesis. And later on I would like to verify my hypothesis, right? That is typically what you do in any experiment, right? You make an hypothesis and then later on you verify whether that hypothesis is true or not. Okay? So I will start with this hypothesis. So I know that this can take 256 possible values. I will make one hypothesis and I will try to verify whether that is indeed my correct key or not. Okay? So this essentially gives me my definition of the hypothetical power. And note that, like what I will try to do now is I will try to use this hypothesis of the power. And remember, I also have my real power trace because I have been capturing the power trace during the encryption process, and I will try to kind of match whether they go together as well. Okay? If they go together, then I will basically bank on the fact that maybe my key guess was correct. Right? So far so good? Any questions so far?
SP and SP++ are the output from SBox.
Yeah, so I am just writing this as a state, but in this case is the output of the SBox. Okay, so this is say ST at this point. Make sense? Okay, so now what we will try to do is we will try to, as I said, also observe the actual power traces. The power traces are also accumulated, and they will be also stored in the form of a matrix. Okay? What I mean is this, that is, suppose I do 1000 encryptions, okay, which means I feed my plaintext 1, I get a cipher, and I also get the corresponding trace. This is my power trace. Remember that graph that we had? So it's a real power trace which you have sampled at certain interval and so on. Likewise, you feed the next plaintext, you get another trace. You have got say 1000 encryptions, you have got 1000 traces. So if you have got these 1000 traces, right, the question is how do you store them, right? So we will form a specific way of storing it, which is very simple. We will store this in the form of a matrix. That means that we will have a matrix of this nature where every row corresponds to an encryption. Okay? Every row corresponds to an encryption. And the number of columns stands for the time instances when you have sampled that power trace. Remember that we are an oscilloscope, we were sampling the real power trace at a certain frequency, right? So you have got some real values, right? So the trace that you have is say corresponding to the plaintext P1 stored in the form of a row in this matrix, where each element over here is a real value. Okay? Likewise, you have got the second row, which is the plaintext over here. That's another like row in the table. And likewise, you have got say 1000 encryptions. Okay? So this matrix, so each column here therefore denotes to say T1, T2. So these are all the time instances. Okay? Maybe you are sampling it till say Tn if there are n number of samples that you have done. So this essentially gives you a matrix which I call as a real power matrix. Okay? This is the real matrix, right? This is nothing but you have stored the power traces in the form of a matrix. Okay? So now what we want is, so let's call this the real power matrix, and what I also want to create in a similar manner is a matrix which I called as a hypothetical power matrix. So what is a hypothetical power matrix? So remember, say consider the first plaintext P1, okay, and you make a guess of the key. Remember this K0 you are trying to find out? So I have made my guess, that guess is a 0, okay, and I find out the S box of P1 XORed with 0, find out the Hamming weight of that, apply my power model, and store this at this location. Make sense? Right? Now I do this for all the plain texts, P2 till P1000. So I get this entire column, right? Then I repeat this process for my next hypothesis, which is 1. I get the next column. I continue to do this for all the possible 255 guesses. So I get essentially a matrix of this nature. Okay? So therefore the number of rows here are 1000 and the number of columns here are 256. So it's a 1000 cross 256 matrix. Likewise, if you see this real power matrix, it's a matrix of dimension 1000 cross n. Right? Does it make sense? Yes? No? Any questions? Because that's it. That's only what you need to do the attack. So if you have understood so far, the next step is super easy.
So why are the dimension of these two not always the same?
Because, okay, the question was, why are the dimensions of these two matrices not the same? Because they are two different things. Okay? So one is a real power trace which you are sampling, which you need to sample, and the other one is based, you are just getting one value depending upon your key hypothesis. They are not the same. Okay? So now what we want is, we want to know among these 256 key hypotheses, which key hypothesis is indeed true, right? We want to know which one is indeed correct. So the issue is, if you observe that, so if I write down all these traces in this manner, so these are the real power traces, say, okay? So out here, note that the actual instance of the S box, okay, takes place at a specific time, which I don't know, okay? But which I hope that is captured in my sampling, because if my sampling is slow, then I may have missed that point actually. So therefore I need an oscilloscope which has got a very high sampling rate. Okay, so it requires typically several gigabits per second. You know, like you need to sample that at a fast rate so that you don't lose that information, right? So assuming that you have that information in your n time samples, then what you will basically need to do is, if I want to verify that whether this hypothesis was correct, I will take this column and I will try to define a similarity metric. It could be a correlation, a simple correlation evaluation, and correlate it with all the columns here. So I will match it with this one, I will match it with this one, and I will match it with all the time instances, like n time instance, and see if there is a good match, if there is a good correlation. Okay? So typically I can use, you know, like Pearson's correlation to begin with, which is a very simple correlation metric. I will soon define again the correlation metric, which you probably already know. Okay, and so this is nothing but a distance metric. So you take two vectors and you find out the distance between them. Okay, so I take this column and I match with all these n columns, okay, of the real power matrix, and I find out or develop another matrix which is called as a correlation matrix. So it's nothing. It's called correlation matrix because I plot the correlations over there. So what I do is, I take this 0th column here in my hypothetical power matrix, which is this one, and I match it with, so I match with the first one, I match with the second one, and so on. Okay? So you can imagine that in this case, say the 0th row of this correlation matrix corresponds to the 0th key hypothesis. Okay? And I match it with all the n time instances. So, you know, I find out the first one, the second one, and so on. So these are all my different time instances. Okay, so I can call it as T1 till say Tn. I repeat this process again for my next key hypothesis. Okay, and likewise I repeat this for all the 256 possible guesses. So now what I want is, I want to verify that among, you know, like, so once I have calculated this correlation matrix, I just need to find out that whether one of these correlations, or which one is higher, which one is, you know, like giving me a maximal value. So the one that gives me the maximum correlation is likely my candidate key. So I will check among all these possible key correlation values, which one, is my, kind of something which stands out compared to the other ones. So if I do correlation plots, you can imagine that there will be small values, but suddenly there will be a peak, and that peak corresponds to your, or at least likely corresponds to your key. That's the idea. Okay. So let me again restate what I said. So what I basically calculate the real power matrix, I calculate the hypothetical power matrix, and I start to calculate this correlation matrix with the hope that the correct key will correlate quite distinctly compared to the others. So this is what I do, therefore. I mean, this is more elaboration of what I said. You find out the power profiles and you store that in the form of some array. So this is a two-dimensional array, basically nothing but a matrix. So you have got a trace two-dimensional matrix which has got number of rows n sample, number of columns n points, which means the time instances when you have sampled them. And then you essentially want to calculate the hypothetical power. Okay. So now one thing I would like to emphasize here in the hypothetical power calculation. Okay. So note that this S box, like this, the one that I was targeting, is easy because here there is no influence of any shift row. Okay. But other rows can. So you just need to kind of accommodate that in your calculation. So once you calculate the hypothetical power and the hypothetical matrix, you store this in the form of this in this matrix. Now in this matrix you have got again n sample instances, because you have got these 1000 encryptions, and you have got number of keys denoting the number of key hypotheses that can take place, which is in our case only 256. Okay. So once you have done this, this is what you are doing. So you have got this the hypothetical power matrix, this is your real power matrix, and you are doing this correlation. So the correlation is in this case shown over here. This is nothing but the Pearson's correlation coefficient. So this I believe most of you know. So this is shown here. So you basically calculate the covariance and divide it by the product of the variance of the two random variables. Okay. So it's nothing but covariance. So if I want to calculate the the correlation between say two random variables x and y. Okay. So let me write it down, x comma y. Then this is nothing but the covariance of x comma y divided by the variance of x and variance of y. Okay. So this is what we just do and plug it over here. That's it. So once you have done this, this is what probably you will get, and we will try to see some of them if you go through the coding exercise that we will soon follow. So here you can see that with number of observations, the wrong key ones, the wrong key guesses, the correlation falls. With more observation, they will fall, but the correct one will peak. Okay, and therefore you can distinguish the correct key from the wrong ones. If you so in this simulation here, I have added more noise. If I add more noise, then the distance is lesser. Okay, and it will take probably more observation to be more confident. Yeah.
Sir, root variance x into root variance per row.
Yeah. So that is fine. Okay, you can just adjust that actually. It doesn't change the relative order of the your correlations. What I want is the to compare two correlation values. Okay. So rather, if you are very precise, then what you can do is tell this is to be proportional to this. Okay. So this is the summary of what we have, and I will stop here for some time. So here you are basically you can do this attack from the plain text or the cipher text. I hope it is visible. And these are all my say 1000 encryptions, or in a general manner say it's D encryptions or D runs of the crypto that you are doing, and these are your key hypotheses. So there are k hypotheses. So in our case, k is equal to 256 when you are talking about AES 128. You apply an intermediate round of the crypto algorithm. So if you are doing it from the plain text, you apply a forward transformation, which is S box. If you are doing it from the ciphertext, you apply the inverse transformation, which is the inverse S box. Make sense? And then you come to the intermediate value. You apply your power model, which is could be Hamming weight, Hamming distance, or some other things. Okay, and calculate the hypothetical power consumption matrix. You have the real power trace, which you sample and create the real power matrix, and then you basically do a correlation analysis. This statistical analysis is nothing but correlation. Okay, and you find out this correlation as shown over here. So here you have the square root if you want. Okay, and so the correct key is this. So the correct key is nothing but you find out the maximum, find out that key. So you basically, maybe I'll just write it down for the sake of, because it may not be very legible. So the correct key is this, that is you return that corresponding ki for which your rkij, that means your correlation, stands out to be the maximum. Okay, among all the possible rkj's, this one is the maximum for all possible runs of k's and j's. Okay, for all k comma j. Okay, so you find out that key which corresponds to the maximum correlation, and you return that as the candidate key. Now this is a statistical attack, which means it may fail as well. But if you increase the number of observations, you will have more confidence in your claim. Okay. Again, this attack is a divide and conquer attack because I have recovered one byte. Similarly, in parallel, I can recover the other key bytes as well. So it doesn't exponentially increase with the key length. Okay. The complexity will be proportional to 2 to the power of 8 in this case. And if you are doing 1 by 1, it will be 16 multiplied by 2 to the power of 8, which is much, much lesser than the brute force complexity of 2 to the power of 128. Okay. So does it make sense so far? So we have basically learned in this module from yesterday 2 techniques. One is difference of mean, and also the other one is correlation power attacks. So I think I will stop here for some time. If you have any questions, you can ask, or we'll go to a bit of, like seeing things actually, like where we'll show you some codes and you can have a look at that and maybe run few experiments and see them. Okay. So any questions?
So why are we taking maximum over to correlation coefficient?
So the idea is that, okay, the question was why are we taking maximum? Okay, so intuitively, right, what we expect that if I have guessed the key correctly, then my estimation of the power, which is the hypothetical power, will match maximally with the real power. Right, and that essentially means that my guess was correct. But if I had guessed wrongly, then maybe sometimes I will correctly estimate, sometimes I will wrongly estimate, and therefore the correlation will be low. Right. So you see, correlation is a funny thing actually. Okay, so if you are always correct or if you are always wrong, then you are always well correlated. Your prediction is good. But if your correlation is bad, if sometimes you are good and sometimes you are bad. Right. So if there is suppose there is a person who makes a guess which is always correct, this is equivalent to a person who makes a guess always which is wrong. Because whatever that person says, you just complement that actually, and you are again good. But in crypto, right, what we want as cryptographers or security designers is that an attacker should be sometimes correct and sometimes wrong. Then he is confused, right? Okay, so I think I will stop here for some time, and we will get back soon. Okay.